Hello and welcome to today's class. Today we'll be looking at the simple theory of elastic torsion. We'll be having a look at, we'll be revising that. We'll be having a look at how to calculate polar second moments of area, and we'll also be looking at the principle of superposition. Okay, so what is the simple theory of elastic torsion? Let's consider a shaft, which might look something like this. We've got our shaft built in at one end. That's attached to a wall here. And if we draw the center line through our shaft, which is going to go through here somewhere, we're going to apply torque T to our shaft, such that a part which initially, let's call it A. So let's say initially A is in this location. And because of that torque, A is moved around to this location. Now let's call that B. Okay, so that has moved through an angle theta. And if we extend this back here, that produces this angle. And the radius of our shaft, let's call that R. Okay, so we've got a point at a position at position A. We're applying a torque on our shaft. Our shaft is of length L. We apply a torque. The material which is at point A moves through this angle theta. It's now at point B. Our shaft is a radius R. Now, what does the simple theory of elastic torsion show? So what we can show is that T over J equals Tor over R equals G theta over L. Now, what do all of those terms mean? Well, T is the torque that we're applying. Okay, now J is known as the polar second moment of area. 4 is our shear stress, the stress on the shaft. R is the radius of the shaft. G is the material stiffness in shear, the shear stiffness. Theta is our angle that we've moved through, and L is the length of our shaft. Okay, so that is pretty much analogous to our simple theory of elastic bending. If we think back to the simple theory of elastic bending, we said M over I equals sigma over Y equals E over R. Okay, M is my moment when we're applying to a shaft in bending. We simply, instead of applying a moment, we're applying a torque, T. I is our second moment of area, and J is our polar second moment of area. And we'll discuss in a minute how we're going to calculate what J is. Sigma is our direct stress, Tor is our shear stress. So as we apply our torque, we're stressing our shaft, but we're stressing it in shear. So we've got shear stress. Y, when we're talking about the simple theory of elastic bending, Y was the distance from the neutral axis. R now is the distance from the center, the radius of the shaft. Okay. And then E is our Young's modulus for our simple theory of elastic bending. Instead of Young's modulus, we've got shear modulus, G, times by theta actually. So it's G theta. So Young's modulus, shear modulus, stiffness in tension and compression, so direct stiffness, stiffness in shear, G. Okay, theta is our angle that we move through, And when we were talking about the simple theory of elastic bending, we talked about the radius of curvature. We're now talking, instead of the radius of curvature, we refer to the length of the shaft that we're twisting. Okay, so T over J equals 2 over R equals G theta over L. Now, sometimes we'll, just like the simple theory of elastic bending, we'll only use two of those terms. So, for example, if we were to ignore that term there, what do we end up with? We end up with T over J equals 2 over R. So therefore, we times through by R. What do we end up with? Our shear stress equals T R over J. Okay, so the stress that we see on our shaft is equal to the torque that we put through our shaft, clearly, the radius of the shaft, they're directly proportional. So if you increase the radius, you're going to increase the stress. So the maximum stress is going to be on the outside of the shaft. Okay, and that's the reason why if radius tends towards 0, stress is clearly going to tend towards 0. So the bit in the middle, it's not really doing a lot. So actually, it's much more efficient when you're putting a shaft into torsion in terms of its stiffness to weight ratio to have a hollow shaft, because the bit in the middle, when radius is very small, it's not really doing a lot. Actually, the material is not very stressed. As R approaches 0, our stress approaches 0, and our shear stress is inversely proportional to J. Okay, so as J increases, stress decreases. So if we increase J, J describes the shaft's resistance to torsion. We increase J, just as I describes a beam's resistance to bending, J describes a shaft's resistance to torsion. So as J increases, so if we've got a large diameter shaft, for example, large diameter hollow shaft, it's got a very high J value. If you increase J, my shear stress is going to go down. So if you've got a large shaft, it's not stressed very much. If you've got a small shaft, if J is very small, then stress is going to increase. Okay, we get more and more stress on our shaft. So clearly, if we're going to use the simple theory of elastic torsion, we need to be able to work out the polar second moment of area. Okay, so the simple theory of elastic torsion simply states T over J equals 2 over R equals G theta over L. Okay, so we're now considering this J, the polar second moment of area. What is J? Okay, think of it as equivalent to I. Okay, I describes the second moment of area describes a beam's resistance to bending, and J, the polar second moment of area, describes a shaft's resistance to torsion. Okay, so we've seen I for a circle. Let's say that's of diameter D. I for that circle. I for the circle was I d to the 4 over 64. Now J for that circle, we now consider J for the same circle. J for that circle is equal to pi d to the 4 over 32. Okay, they're very similar. I always get them confused actually. So you don't need to remember that, but you should certainly be able to recognize that I, the second moment of area for a circle, pi d to the 4 over 64, and J for a circle, pi d to the 4 over 32. Okay, and as I was saying earlier, quite often when you're looking at a shaft in torsion, the bit in the middle doesn't really do a lot. Okay, so we've seen my shear stress to tor equals T R over J. So as the radius approaches 0, the stress approaches 0. So the bit in the middle of the shaft doesn't really do a lot. So a lot of the time we'll actually end up with a hollow shaft when we're dealing with a shaft which is transmitting a torque, whether that be a prop shaft or whatever. Often we'll have a hollow shaft because as radius approaches 0, radius is the distance from the center, as it approaches 0, the shear stress approaches 0. It's not really doing a lot. So clearly we're going to need to be able to calculate J for this section, for a hollow section. Okay, and in order to do that, we'll use the principle of superposition. Okay, so we've seen J for each circle is pi d to the 4 over 32. So if we've got a solid section, we know how to work out what J is. Okay, J equals pi d to the 4 over 32. If this is this outside diameter, I've called that capital D. Okay, now this inside this circle here, this was a solid circle of diameter small d. Okay, J would be pi small d to the 4 over 32. If we simply subtract one from the other, what we end up with is the bit that's left, the difference, this bit here. Okay, and that's the principle of superposition. So all we would say there is for the entire section, it's equal to pi d to the 4 over 32 minus pi small d to the 4 over 32. Okay, and if we factorize that, we've got pi over 32, and we've got d to the 4 minus d to the 4. Okay, so often we'll actually use the principle of superposition, and we'll simply say this. If we want to work out the second moment of area for our shaft, let's simply take the outside diameter, raise it to the power of 4, subtract the inside diameter, raise it to the power of 4, times it by pi over 32, and that's going to give us this red shaded region here, the difference. That's the principle of superposition. So let's have a look at some examples using the simple theory of elastic torsion. Question number 1. A solid shaft 100 millimeters in diameter transmits 75 kilowatts at 150 revolutions per minute. Determine the value of the maximum shear stress set up in the shaft and the angle of twist per meter of the shaft if G is 80 gigapascals. Part B. If the shaft were now bored in order to reduce weight to produce a tube of 100 millimeters outside diameter and 60 millimeters inside diameter, what torque could be carried if the same maximum shear stress is not to be exceeded? What is the percentage increase in power to weight ratio affected by this modification? Okay, so question number 1. We've got a shaft, solid shaft, 100 millimeters in diameter. There's my shaft, and the diameter is 100 millimeters. Power equals 75 kilowatts. The angular speed is 150 revolutions per minute. And G, the shear modulus, is 80 gigapascals. So What are we going to need? We're looking at determining the value of the maximum shear stress. So looking at the simple theory of elastic torsion, we know T over J equals 4 over R equals G theta over L. Okay, so we're simply going to use for this first part, we've got power and angular speed, therefore we can work out torque, we can work out J, you know, the radius of the shaft, so therefore we can work out the shear stress, so we can ignore this part here. Okay, so we're simply going to say 4 equals T R over J. So clearly we need to know T, we need to know J. So first thing we're going to calculate is our torque. Now we know power equals our torque times by our angular velocity. Okay, we know that from our dynamics. Our dynamic lectures, power equals torque times by angular velocity. So therefore our torque equals our power, 75 kilowatts, over our angular velocity. Now we know that this is traveling at 150 revolutions per minute. Clearly we need to transfer that into radians per second, but we've got our angular velocity. So our power, 75 times 10 to the 3, 75 kilowatts, divided by our angular velocity was 150 revolutions per minute, times by 2 pi, how many radians per minute, divided by 60. It's going to be that many radians per second. Okay, and if we calculate that, we get 4.77 kilonewton meters. Okay, that's the torque going through this shaft. Okay, so we've got P now. R is the position where we're calculating the stress. The maximum stress is going to be when R is our maximum, so it's going to be on the outside surface of this shaft. So we're going to take R as, remember this is 100 millimeters diameter, so we'll take R as 50 millimeters, the outside radius of this shaft. So we need to know J still. We need to calculate J. Now we know J equals pi b to the 4 over 32. Okay, pi times by the diameter of this shaft, 100 times 10 to the 4. Oh, sorry, 100 raised to the power of 4. That's in millimeters, so we need to times that by 1 times 10 to the minus 12 millimeters to the 4. So we're going to get times 10 to the minus 3 raised to the power of 4. So times 10 to the minus 12 divided by 32. It's going to give me a J value 9.82 times 10 to the minus 6 meters to the 4. Okay, so now that we've got T and J, we can look at this and we can simply work out what are my shear stresses. So torque equals T R over J equals my torque, which is 4.77 times 10 to the 3, which I calculated here, times by my radius. Like I say, we're going to assume that's 50 millimeters, so 50 times 10 to the minus 3 divided by my J value, which we just calculated there, 9.82 times 10 to the minus 6, which means the shear stress on the outside of this shaft transmitting that power at that speed is going to be 24.3 megapascals. So the next part of the question asks us what is the angle of twist per meter in the shaft. Okay, now we know from the simple theory elastic bending, or simple theory elastic torsion, d over j equals 4 over r equals g theta over l. Okay, so this time we're going to use d over j equals g theta over l. Okay, so t over j equals g theta over l. I rearrange that by times through by l, divide through by g. I'm going to end up with theta equals TL over GJ. Okay, now my torque, we worked out in the first part of the question, was 4.77 times 10 to the 3. L, the length of our shaft, now we're asked to calculate the angle per meter, so that will be 1 meter, divided by G. We're told it's 80 gigapascals, so 80 times 10 to the 9, divided by, times by J. J we've also worked out in the first part of the question, 9.82 times 10 to the minus 6. And if we calculate that, we get 6.07 times 10 to the minus 3 radians per meter. Now, if we times that by 316 divided by pi, we'll end up with degrees per meter. So 6.07 times 10 to the minus 3 times by 360 divided by 2 pi gives me 0.348 degrees per meter. Okay, so that answer there is correct. This one is potentially easier to relate to. Just over 1/3 of a degree per meter. That's how much this shaft would twist during this torque. Okay, part B. So we've now hollowed out this shaft in order to get a more efficient shaft in terms of power to weight ratio. So we've got our shaft, and we've hollowed it out. The outside diameter is 100 millimeters still. And the inside diameter, the bore, is 60 millimeters. Okay, so got a new J value. It's actually slightly smaller. We've removed some material, so J is going to twist more, but actually the bit that we've removed is the least efficient bit, the bit in the middle. Okay, so J for our hollow shaft equals 532 outside diameter raised to the power of 4 minus inside diameter raised to the power of 4. So that's going to be 532 100 to the 4 minus 60 to the 4, and that's all going to be times by 1 times 10 to the minus 12. Get that from millimeters into meters. So that's going to be 8.545 times 10 to the minus 6 meters to the 4. Okay, now the J value before was 9.82 times 10 to the minus 6. It's now gone down to 8.5 times 10 to the minus 6. Okay, so it is going to twist more, but it's going to be a lot lighter because we've removed that material. So what torque can we now carry if the same maximum shear stress is not to be exceeded? That's what the question is asking us. So what do we know? We know T equals tor J upon R. That's material elastic bending. The same torque, shear stress, sorry. The shear stress was 24.3 times 10 to the 6, 24.3 megapascals. That was the first part of the question. J has reduced to 8.545 times 10 to the minus 6. And the radius, again, maximum shear stress is going to be on the outside of the shaft, so we'll take 50 times 10 to the 3 times 10 to the minus 3 gives me 4153 Newton meters. Okay, so before the shaft was carrying 4.77 kilonewton meters. Now the shaft is carrying 4.15 kilonewton meters. Okay, so the amount of torque that the shaft can carry for the same stress has gone down slightly because the J value has gone down slightly because we bored it out. Okay, so the second part of the question then says, what was the percentage increase in the power to weight ratio affected by this modification? So let's now have a think about that. So the torque that we can carry actually has gone down slightly because we've hollowed this shaft out. But let's now think about the stiffness to power to weight ratio. Okay, so let's look at the original shaft first of all. Okay, so original shaft. Now the weight per meter equals pi r squared or pi d squared divided by 4. So that's going to be pi over 4 times by the diameter 100 squared times 10 to the minus 6. So that's the area of the shaft, pi r squared or pi d squared over 4 per meter. So times by 1. It's going to be the volume of the shaft times by the density times by gravity to get volume to mass to weight. Okay, so that's going to be the weight of the shaft per meter, 7.854 times 10 to the minus 3 rho g. And that is our weight per meter. So therefore, the power to weight ratio for 1 meter is going to be, okay, so the power is the torque times by the angular speed. So that's 4.77 times 10 to the 3. That's the torque that we were transmitting times by omega. Give us the power. In the first part of the question, that was actually 75 kilowatts, wasn't it? So torque times by power divided by the weight per meter, 7.854 times 10 minus 3 rho g is going to give us 6.073 times 10 to the 5 times by the angular speed divided by rho g. So that is the power to weight ratio for the original shaft. Now the new shaft, let's calculate this in the same way. So weight per meter equals pi over 4 times by 100 squared minus 60 squared times 10 to the minus 6 times by 1 times by rho g gives me 5.0 0.27 times 10 to the minus 3 rho g. And the power to weight ratio. This shaft can now only carry 4.15 times 10 to the 3. That's the torque that it can carry. That's what we calculated in the first part of the question. Times by omega divided by 5.027 times 10 to the minus 3 rho g. So for our new shaft, we've got 8.255 times 10 to the 5 omega over rho g. Omega over rho g, clearly that's the same for both shafts. So it's these numbers that we're interested in. Okay, so the question asks us what is the percentage increase in the power to weight ratio. So percentage increase is going to be the difference divided by the original value. So that's 8.255 minus 6.073 divided by 6.073, which is 0.36 or 36%. Okay, so the power to weight ratio is increased by 36% by doing this. Question 2. Determine the dimensions of a hollow shaft with a diameter ratio of 3:4, which is to transmit 60 kilowatts at 200 revolutions per minute. The maximum shear stress in the shaft is limited to 70 megapascals and the angle of twist to 3.8 degrees in a length of 4 meters. Okay, question 2. Now we've got a hollow shaft. Let's write down what we're told in this question. We've got a diameter ratio of 3:4, so the inside diameter divided by the outside diameter, 3 divided by 4, that's a quarter, 3/4, 0.75. Okay, what else are we told in the question? It transmits a power of 60 kilowatts. So our power equals 60 kilowatts. Our angular speed, transmitting that at 200 revolutions per minute. Again, we're going to have to convert that to radians per second. And we're told a couple of conditions. We want to limit the maximum shear stress in the shaft to 70 megapascals. So the maximum shear stress we want to see is 70 megapascals. And the maximum angle of twist is 3.8 degrees over a length of 4 meters. What we're not told in the question, actually we would need in this question, is what is G? What is the shear stiffness? Clearly we need to know how stiff this material is that this shaft is made from. And what we're going to assume is that this is 80 gigapascals. Okay, let's assume it's made from steel or something like that. Okay, so G is 80 gigapascals. So we need to consider those two conditions. The first condition is that our maximum shear stress is 70 megapascals. The second condition is that the maximum angle of twist is 3.8 degrees, okay, over this 4 meter length. And our ratios of diameters is 3:4, 0.75. Okay, so let's consider our first condition. Okay, so what are we going to use? We're simply going to say T over J equals 4 over R. We're going to use that. So let's rearrange that we're going to end up with J equals TR over Tor. So clearly we need to know what torque we're transmitting, radius of the shaft, and the shear stress. Shear stress we're given in the question, the radius of the shaft, clearly we need to calculate that. Okay, so first of all, what is T? What is the torque that we're transmitting? Well, we've already said that power equals T omega. So therefore, T equals power divided by omega. So our power is 60 kilowatts, 60 times 10 to the 3. And our angular speed, well, it's 200 revolutions per minute, times by 2 pi, that many radians per minute, divided by 60, it's going to give us that many radians per second. So our torque is 2.86 times 10 to the 3 Newton meters. That's the torque that we're transmitting with this power and this angular speed. Okay, so we've got T. So we know from our torsion theory that T over TR divided by our shear stress is equal to J. Now, what is J? So J is pi over 32 times by the outside diameter raised to the power of 4 minus the inside diameter raised to the power of 4 equals our torque 2.86 times 10 to the 3 times by our radius, which is our diameter, divided by 2. So we have 2 on the bottom. On the bottom, we've also got our shear stress, which we're asked to limit to 70 megapascals. So we'll also have 70 times 10 to the 6 on the bottom. So we've now got an equation with 2 unknowns in it, large d and small d. However, we do know how they're related. We know that d over d is 0.75. So therefore, d equals small d. So d over d equals 0.75. So therefore, d equals 0.75 times by the diameter. So if we go back to this equation here, we can rewrite that as pi over 32 d to the 4 minus 0.75 to the 4 d to the 4. Equals, calculate that, what do we get? 20.43 times 10 to the minus 6 times by large d. Okay. So pi over 32, bring b to the 4 outside of that, we can factorize that. 1 minus 0.75 to the 4 equals 20.43 times 10 to the minus 6 times by d. So 0.06711 d to the 3 equals to 0.43 times 10 to the minus 6. D cubed, we'll divide through by that. It's going to be 304.4 times 10 to the minus 6. Therefore, D equals 0.0673 meters in SI units, or 67.3 millimeters So that's our first condition. So in order to limit our shear stress to 70 megapascals, which we're asking the question there, we've used that there, 70 megapascals, so we're limiting it to 70 megapascals. Our outside diameter needs to be 67.3 millimeters. Let's now have a look at that second condition. We want a rotation, a twist of 3.8 degrees over this 4 meter length. Okay, so this time, instead of using our shear stress, we're going to be thinking about our angle. Okay, so this time, again from the simple theory of elastic torsion, T over J equals G theta over L. So therefore, J equals T L over G theta. Let's do the same thing. Let's put those numbers in now and work out for this particular condition, 3.8 degrees twist over this 4 meter length, what outside diameter we would need. Okay, so J is pi over 32. Outside diameter to the 4 minus inside diameter to the 4 times by my torque, which we've calculated in is equal to my torque, which we calculated in the first part of the question, which was 2.86 times 10 to the 3. It's by the length of this shaft, 4 meters, divided by G, which we've got as 80 gigapascals, 80 times 10 to the 9, times by my angle, which 360 over 3.8 times by 2 pi. So we've converted from radians to degrees there. So from degrees into radians. We also know again that D over D equals 0.75. So therefore, D over 32, e to the 4, lots of 1 minus 0.75 to the 4 equals 2.156 times 10 to the minus 6. So therefore, e to the 4 equals 32.12 times 10 to the minus 6, or D is equal to 32.12 times 10 to the minus 6. That's 32.12, sorry, okay, so yeah, that's D to the 4. So therefore D equals 0.0753 meters, or 75.3 millimeters. So for the first condition, when we were limiting the stress to 70 megapascals, our outside diameter needed to be 67.3 millimeters. But in order to limit the angle of twist to 3.8 degrees, our shaft actually needs to be 75.3 millimeters. So that's the limiting factor in order to limit both, or to meet both of those conditions. Therefore, D must be equal to 75.3 millimeters. Because if it's less than that, the angle of twist will be exceeded. Even though the shear stress isn't exceeded, the angle of twist would be exceeded. Okay, so D equals 75.3. Now, we know that small d equals 0.75 times by big D, which is 0.75 times by 75.3, which gives me 56.5 millimeters. That's going to be the inside diameter. Question 3. A shaft 50 millimeters in diameter and 0.7 meters long is subjected to a torque of 1,200 Newton meters. Calculate the shear stress and the angle of twist. Take G as 90 gigapascals. Question 3. Okay. So this is quite a simple question. We're going to use the simple theory of elastic torsion. So T over J equals Tor over R equals G theta over L. Okay. Now, in this scenario, what have we got? We've got a shaft. 50 millimeters in diameter. So diameter is 50 millimeters. It is 0.7 meters long, so 0.7 meters long. We built in at one end. Then a hollow shaft. Sorry, question 3. Shaft 50 millimeters in diameter, 0.7 meters long, subjected to a torque of 1,200 Newton meters. So my torque equals 1,200 Newton meters, and the G value, shear stiffness, G is 90 gigapascals, and we're asked to calculate the shear stress and the angle of twist. So in the first part of the question, the shear stress, we're simply going to say that Tor max equals TR over J. Because we're going to ignore that bit. We're going to concentrate on those two parts on the simple theory of elastic torsion. Shear stress, so times 2 by R, TR over J. My torque, 1,200 times by the radius. This thing is 50 mil diameter, so the radius is 25 times 10 to the minus 3 divided by J, which is pi over 32, so pi 32 will be on the top, therefore, times by the diameter raised to the power of 4. So that's going to be 50 times 10 to the minus 3 raised to the power of 4 gives me 48.89 megapascals. And then the second part of the question, we're asked to calculate theta. So therefore, this time we need to look at this term. So we're going to say, therefore, theta equals Tor L over R G. So we're ignoring this part. We're looking at these two terms. Theta equals Tor L over R G. My shear stress we've just calculated, 48.89 times 10 to the 6 times by the length of the shaft we're told in the question, 0.7, divided by the radius that we're considering, so 25 times 10 to the minus 3 times by G, which we're told in the question, 90 gigapascals, 90 times 10 to the 9. If we do that lot, we get 0.0152 radians. And as usual, we might want to put that into degrees to make that more understandable to us. So 0.0152 times by 360 divided by 2 pi gives us 0.871 degrees. Question 4. Repeat the previous problem, but this time the shaft is hollow with an internal diameter of 30 millimeters. Comment on the results. What is the weight save? Question 4. Okay, so first thing we need to do is to calculate the shear stress and the angle in the same way that we did in the previous question. Okay, so T max equals T R over J. T and R clearly remain the same. The only thing that we've changed in this question is J. We've now hollowed this shaft out. Okay, so this sum is going to be exactly the same. 1200 times by 25 times 10 to the minus 3 times by 32 divided by pi times by 50 to the 4. Last time we just did 50 times 10 to the 4, but this time we're going to use the principle of superposition, so we're going to subtract the middle bit 30 to the power of 4 times 10 to the minus 12. It's going to give us 56.17 megapascals. So before, when the shaft wasn't hollowed out, the shear stress was 48.89 megapascals. Now we've hollowed it out, it's gone up to 56.17 megapascals. So the shear stress has gone up slightly. Theta, again, it's going to be exactly the same. 4L over RG. The only thing that's changed now is that my shear stress has increased from 48 megapascals up to 56 megapascals. So we've got 56.17 times 10 to the 6 times by 0.7 divided by 25 times 10 to the minus 3 times by 90 times 10 to the 9. So that sum is exactly the same as before. The only thing that's changed is my shear stress has increased. And so because of that, my angle was increased to 0.0175 radians, which is 0.0175 times by 360 divided by 2 pi. That is actually 1 degree. Okay, so before the shaft twisted by 0.87 degrees, it's now twisting by 1 degree. So the question then goes on to ask us, comment on the results and to work out the weight save. So let's do that. So our weight save is simply going to be, assuming it's made, both shafts made from the same material, is going to be the ratio of the volumes. Okay, so our weight save is simply second volume divided by the first volume. Our second volume, sorry, is going to be pi r squared minus r squared. Big R is the outside radius, small r is the inside radius, times by the length. That's the original volume. Oh, sorry, that's the new volume. And the original volume is going to be pi r squared times by L. Okay, now clearly we can simplify a lot of that. Pi cancels out. The shaft is of the same length, so we're going to end up with r squared minus r squared divided by r squared, which is equal to 25 squared minus 15 squared divided by 25 squared equals 0.64. So it's 64% of the weight. So what do we get? Therefore, 36% weight save. Okay, 1 minus that, 100% minus that 64% gives us our 36%. Now, so our weight save, we'll see a 36% weight save. We're also asked to comment on the increasing stress and the increasing angle. Okay, so let's consider our stress first of all. Increase in stress. So Our new shaft seeing 56.17 megapascals. Our old shaft was only seeing 48.89 megapascals. So that is 1.15. So therefore, a 15% increase. In terms of stress. We're also asked to comment on the angle. Increase in angle. 1 divided by, so new shaft is deflecting by 1 degree, twisting by 1 degree. The old shaft was 0.871 degrees, which is also 1.15. So there's obviously a 15% increase. Okay, obviously the angle is related to the stress. But what do we see with this modification? Okay, so we're seeing a 36% weight save by boring out this shaft. We see a 15% increase in stress, a 15% increase in angle, but a 36% weight save. Now, obviously, that can be beneficial to us in certain applications. So, what have we covered there today? Simple theory of elastic torsion, T over J equals 4 over R equals G theta over L. Okay, P is the torque going through the shaft, J is the polar second moment of area, 4 is the shear stress on the shaft, R is the radius of the shaft, G is the shear modulus, the stiffness of the material in shear, theta is the angle that the shaft is twisted through, and L is the length of the shaft. Okay, any questions on any of that, let me know, and hopefully I can help you. Okay, bye-bye.